industry track. The title is Jointly Optimize Capacity, Latency, and Engagement in Large-Scale Recommender Systems. This is going to be presented by Hitesh Khandelwal from Facebook. Whenever you want, you can start.
Right. Hey, everyone. This is Hitesh from Facebook. I work in commerce infrastructure team responsible for building recommendation systems for Facebook Marketplace. In this talk, I will share how we built our recommendation system to jointly optimize for compute capacity, user perceived latency, and engagement. We implemented this idea in production for Facebook Marketplace, but the concepts and principles are generic and can be applied to any recommendation-based system like videos ranking as well. For some context on Facebook Marketplace first, it is a tab inside the main Facebook Blue app. And when you click on this tab, you see a recommendation feed of shoppable items, as you can see in the figure on right. For some context, Facebook Marketplace is used by 1 billion users every month. So yeah, we work on pretty high scale from that point of view. Let's talk about the 3 dimensions we are going to optimize and lay out the problem statement a bit. The first dimension is ranking-driven recommendations helps connecting buyers with the products they love, also measured in form of engagement. The second dimension is a runtime latency. We need fast user experience for a successful product measured in form of latency. And the third dimension is computational cost or capacity demand needs to be low for a sustainable business growth and product growth. Our goal here is to optimize for the capacity and latency to scale our system for sophisticated ML models. Important to note that there's a constant trade-off between these 3 dimensions. So finding a good balance between them is quite important. Flexibility is also important because business needs can change over time. For example, COVID triggered a global supply chain disruption, which has caused hardware server supply crunch everywhere. This is a industry standard 2-stage recommendation system where the first stage is retrieval of top candidates from your indexes. This stage uses cheaper and simpler ML models, while the second stage is for ranking, which uses complex neural network with multiple layers and lots of dense and sparse features. The cost of the second stage, which is the ranking stage, is naturally the highest. So our goal here is to optimize the cost and latency over here. And one of the most common optimization technique is caching. In the standard approach, we cache the ordered list of items for each user. And when the same users comes back again, we show items from this ordered list. Naturally, this gives large capacity and latency savings. But the problem, though, is that it comes with staleness, also known as gap time, which can negatively impact your engagement quite a bit. We'll talk about gap time a bit more, but the drop makes sense in engagement because we are serving stale experience while users are expecting a more fresh experience. Now let's get into this gap time issue a bit more, which is defined as the time difference when the score or feature was generated in the backend versus the time when the event was generated because of user activity on the recommendation feed. For example, if we rank and cache an item for a user at T1, and when the same user comes back and we show that cached item at T2, there's a gap between these 2 timestamps, and that's the gap time. High gap time can negatively impact your ranking quality at training time because it's just simply incorrect to use the stale features. As you can see in the picture below, we are joining the training data label with the features which were generated when the item was put into the cache, which could be long time back. Oh. Similarly, gap time can impact the ranking quality. I think I moved quite a bit slides. Similarly, gap time can impact ranking quality at the serving time as well, because it's incorrect to use the stale scores later in future. Again, as you can see in the picture below, we are using the stale scores, which was generated when the item was put in the cache and using it later in future. So our approach to fix this problem with the training time is to optimize the ranker model performance under fresh conditions, assuming there's no gap time. There are two ways you can do that. First approach is you can simply remove the training data with high gap time. This is simple approach, but you need to be careful with the training data loss in terms of volume. But more importantly, you need to make sure there's no bias introduced in your training data by removing such samples. A more sophisticated approach is to regenerate the features at the training time, as you can see in the picture over there. This is a bit more complex, but it avoids all the training data loss problems. In our experiments, we do not see any noticeable difference between these two options. Now, our approach to solve this gap time issue at the serving time is to adjust the cached scores given the gap time. So towards that approach, we introduce a new lightweight ML model, we call it adjuster, whose job is to predict the fresh ranking score given for those cached items, given the old ranking score, gap time, and a handful of features. Our adjuster model is 10 times cheaper in size and compute capacity than the full ranker model. And that's where most of the savings in our works comes from. We model it as a knowledge distillation problem where the full ranker model serves as the teacher and the smaller adjuster model is a student of that model. And lastly, there are only a handful of features which we used in adjuster, mostly time-sensitive ones like the CTR of delta of 1 hour. This is the overall solution. We call it Smart Cache. In this solution, for each user, we cache items with their ranking scores, in addition to their ordered position in that ordered list. And when users come back, the same user comes back in future, we reuse those cached items, but after adjusting their cached score with the lightweight ML model, which we call adjuster. In terms of system flow, we do the retrieval as usual, but we use the full ranker model for the new candidates, which were never seen before as usual. But we use the lightweight adjuster model for the cached candidates, which we have seen in past and have cached them. And finally, we merge the two sets to create the ranked feed. This approach avoids a repeated re-ranking of the same item, which gives us big capacity savings similar to the standard cache approach. But unlike the standard cache approach, we have also solved for the staleness, which will help us recover the engagement drop. In our production deployment, we observed 50% capacity reduction after this launch. Now to optimize latency, we introduce a new technique where we can prefetch the ranked feed ahead of time before even user opens the marketplace tab. And when they do actually visit the marketplace tab, the content would just be there and the user latency would be really low and nice. But the problem with this naive approach is that it increases capacity demand quite a bit because the probability of person clicking on marketplace tab is not super high. So to solve this problem, we will be leveraging the Smart Cache, which is note that 10 times cheaper than the full ranking. We also built two ML models to predict or decide whether to prefetch or not prefetch the feed. The first model predicts the probability of user visiting marketplace, and the second model predicts what would be the user perceived latency. And if the both probability of user visiting and the perceived latency are high, then actually we do prefetch only from the Smart Cache and not doing the full ranking. What we observed after production launch is that the latency was reduced by 35% in addition to the 50% capacity reduction. So finally, we combined all the techniques we developed to jointly optimize for the 3 dimensions we talked about to achieve a global maxima. As I mentioned in the beginning, more often than not, there's a constant trade-off between the 3 dimensions. So it's important to find the right balance between them. In our solution, we tune the gap time and the prefetching threshold to find the right balance. For detuning these parameters, you can either do the simple grid search, but then you have to run a lot of A/B tests to do that. Or you can do more efficient Bayesian constraints optimization, which will converge much faster than the simple grid search. At the end of the day, what combination of trade-off and parameter works for you, you have to decide based on your business needs and system requirements. But for marketplace, we were able to get capacity reduction of 50%, latency reduction of 35% with almost no noticeable drop in engagement. That's it from my side. I do want to mention again that although we deployed this in production for Facebook Marketplace, the concepts and ideas are generic and applicable for any recommendation-based system. So happy to take more questions and talk about it. Thank you.
Thank you, Hitesh, for your presentation. We have a question, more than one, from the remote audience. So first is, if you gauge results per user, how do you introduce new items? Is that also part of the adjuster?
That's a good question. So there are different ways we can leverage this smart cache. And one of the way we leverage is, as I mentioned in my slide, one of the slides is we do not change the retrieval. So when the user visits next time, again, we'll do a fresh retrieval completely. And that will surface the new inventory if there's a new inventory which is relevant for that user. But to figure out what is the top 5 of top 10 items we need to show, that's where the ranking comes, and that's where the stage 2, the adjuster, comes into the picture to optimize the cost. So yes, we do allow new inventory to be introduced for a user.
Mm-hmm. Thanks. Another question by Atya Radwan is, how do you make sure that feature regeneration and joining wouldn't cause a feature from the future leak?
Yeah, that's a really great question. Definitely, we spend a lot of time thinking about that part. So what we try to do, we have built a system where you can actually kind of go back in time just before when the user event or label was generated. So we kind of keep some recent history of last 1 hour, so which allows us to go before that event label. Otherwise, if we generate those features after the event has happened, definitely there will be a leakage, and that will introduce quite a bit of bias.
Okay. So one more question from Michael Pulis. Is it possible, I mean, do you account for the user interest drift? Is that something that can cause a problem? Is that not an issue, perhaps depending on what is the actually length of the time gaps?
Yes, definitely. Again, it's all then finding the right balance. The gap time could be in minutes to hours to days, which allows you to figure out what is the right mix of diversity you want for each user experience. But it's tunable depending on your needs and requirement.
Okay, thanks a lot. Let's
thank you.
Our speaker again. And then last,